Hello and welcome to Chemistry Lesson 2.02 on atomic structure. In this lesson, we're going to review the overall structure of the atom along with the values that we ascribe to that structure as in atomic number and atomic mass. So the particles that we're talking about, you probably remember you've done this in junior high, you would have done this freshman year. But if we look at the structure of an atom, the diagram that you guys have always seen is a nucleus that's composed of particles. And let's pick some different colors here. And around that nucleus, we have, you guys called them maybe orbits, circular paths that go around. And inside of that, you have electrons. So this should seem familiar to you. What we're going to learn this year is that this model is really, really oversimplified. I'm going to change these to green. I think I want green here instead. And the reality is a little bit more complex. And until now, you really haven't had the time to consider it or you have the time to give to it. So in the nucleus, we have protons and we have neutrons. And around in the orbit, we're going to learn they're actually called orbitals. We have electrons. So the symbols that we use for proton, and we're going to use these quite a bit, is a lowercase p with a plus, a lowercase n with a 0, and a lowercase e with a negative. Well, why? What do these symbols mean? They correlate to the charge. So an electron has a charge of -1, proton has a charge of +1, and the charge on a neutron reminds me of a joke I heard where a neutron walks into a bar and asks how much for a beer. The bartender says, "For you, no charge." Ba-dum-bum. Okay. So a neutron does not have an overall charge. So we say the neutron has a 0 charge. And when we use this +1, that's kind of an arbitrary. Scientists do this very often. They'll say, we're just going to take the charge that's on a proton and we're going to say that's the value of 1 to make it easier to work with. So a lot of times people say positive and negative, but there's actually a number associated with that. So you're talking about a +1 and a -1. Now, what about mass? So when we talk about the mass of protons and neutrons, the actual mass of a proton and a neutron is 1.67 times 10 to the -27th kilograms. It's a really, really small number. Kind of like people, we can use different scales to measure mass. So for us, we can talk about our mass in kilograms or in pounds or in something called stones in the English system. Well, we're going to look at something called electron volts, EVs, and it's not something we're ever going to use again, so I'm going to write it in black. But if you look at the mass of a proton, that has 900 EVs, and a neutron has 900 EVs. So they are identical. Their mass is identical. So if I looked at the actual mass of a neutron, it would be 1.67 times 10 to the -27th. The reason is protons and neutrons are made of smaller particles called quarks, Q-U-A-R-K-S, and those quarks all have the same mass. But when we put quarks together in different ways, it gives us different charges. But if you look at the mass of an electron, that is 1/2 of an electron volt. So protons and neutrons are almost 1,000 times more massive than electrons. Interestingly enough, though, the charges are equal and opposite for protons and electrons. And indeed, we find the protons and the neutrons in the nucleus, and they're held together by, it's called a nuclear force. But the electrons are found far away from the nucleus, and they do, in a sense, move around the nucleus, but not in the way you've been led to believe, where they orbit like little planets around the sun. But that's about 3 chapters from now, so we're not going to get too far down that rabbit hole. We represent the elements on the periodic table, and if you, on your paper at the bottom of this page, you have a small periodic table. If I take one block from that periodic table, it's going to look like what we see here, where I have the atomic symbol. I'm just going to underline this in yellow. The atomic symbol is in the center, and there I have helium. Remember, for atomic symbols, the first letter is always capitalized and the second letter is always lowercase. To write it any other way would be to write it incorrectly. So my atomic number is equal to the number of protons in an element. And if I look at, let's put a couple others over here. So let me do zinc, Zn, and let me do mercury, Hg. The atomic number for zinc is 30, and the atomic number for mercury is 80. That means that zinc has 30 protons in the nucleus, and mercury has 80 protons in the nucleus. So you can see we have quite a difference in numbers of protons. In fact, we have 118 elements on our periodic table. So if you look below, that last block is 118. And the atomic number is not only the number of protons, but we can talk about the atomic number or the number of protons being equivalent to, we're talking about protons here, so I'm going to go back to my pink color. Protons give an element its place in the table. And in a sense, its identity. We can change the number of neutrons and have the same element. So this can change. And this can change. And you can still have the same element. But if you change the protons, you change the element. If I take away a proton from this helium, so if I came in here and I kicked one of these pink guys out, this is actually lithium because it's got 3 protons, and so I know that this has got to be lithium. So if I kicked one of these guys out, that would be helium because it would have 2. If I kicked 2 of those protons out, I would have hydrogen because it would have 1 proton. So if you change the number of protons, you're changing the element that you're talking about. If you can change the neutrons, and that changes the weight. You can change the electrons, and that changes the charge. But you cannot change the number of protons and still maintain the same element. All right, well, what's this guy down here? We have the atomic mass. The atomic mass is the protons plus the neutrons. Well, what about the electrons? Why they get left out of the deal? Remember, they barely have any mass at all. They have a half of an electron volt compared to, if we add these two together, 1,800. Losing an electron as it relates to an atom, if you got on a scale and you took your mass, you got off the scale and you pulled a hair off your head and you got back on the scale and you took your mass again, would you see a difference in your weight or your mass? And the answer is no. A hair just doesn't weigh enough to make a difference. And that's what's true for electrons. So when we find the atomic mass of an element, we add up the total number of protons. We should probably write that, total number of protons and the total number of neutrons. Well, if this is the protons plus the neutrons, so this is P plus N equals 4, and I have 2 protons, 2 plus what number is going to give me 4, that must mean that my neutrons here are 2. So we can find the number of neutrons by taking the atomic mass minus the protons. Turns out these are my atomic numbers. So we always write that up top. Let me do this in the box so it looks familiar to you. We have the symbol here, Zn. Turns out my atomic mass for zinc is 65 for this isotope. If you look on the table, you'll notice that there's a bunch of decimals, and we'll talk about that in the next chapter, why that is. If I look at this isotope of mercury, I'm going to have a number of 200. So if I take, remember, this is my protons here, and this is protons plus neutrons. So if I subtract 80 from 200, that means that this isotope of mercury is going to have 120 neutrons, and it means that this isotope of zinc is going to have 35 neutrons. Well, wait, don't the protons and neutrons have to be equal? No, they do not. In fact, they rarely are. For the smaller elements, that's more the case, but for as we get up into metals and more complicated elements, we do not. So if I take 80 protons plus 120 neutrons, that's going to give me 200. If I take 30 protons plus 35 neutrons, it's going to give me a mass of 65. So that is an explanation of the overall structure. Our takeaways here are that we're going to need to know the charge, location, and symbols for protons, neutrons, and electrons. It's okay to think of it like this for now, but that's going to be changing. And then we also need to take away a pretty good understanding of atomic mass, atomic number, and how you can use the atomic mass to find the number of protons. All right, thanks for watching and have a good day.